This sweeping beam of light over a contracting human iris represents a largely unseen layer of American infrastructure. While many countries track their populations using visible systems like passports, national ID cards, or central registries of births and deaths, the United States relies heavily on human biological markers. For decades, the engine powering this entire biometric security apparatus was a legacy database known as IDENT. It grew quietly in the background, absorbing millions of physical records over its lifespan. Governments eventually realized that relying on what people carried in their pockets, pieces of paper or plastic cards, was highly vulnerable to fraud. So they stopped tracking the documents and started tracking the physical geometry of the people themselves. This chart maps out a volume curve scaling upward over time, telling the story of how that system grew. In the 1990s, IDENT started as a simple tool for immigration officers to check fingerprints against a small list of prior encounters. But as demand for biometric verification increased exponentially, that curve pushed past 250 million unique identities. To handle those identities, IDENT relied on classic enterprise architecture. It was built on a traditional Oracle relational database. This meant every piece of biographic data, names, dates of birth, encounter logs, was meticulously organized into neat rows in text tables. But physical biometrics cannot fit neatly inside text tables. The actual fingerprint images and facial photos had to be stored externally. Depending on the era, these records were dumped into massive proprietary binary files, or unstructured blobs, binary large objects, sitting completely outside the organized rows. And the database itself couldn't process those images. To actually match a fingerprint, IDENT had to send the data through thin, highly constrained pipelines over to separate hardware appliances built by third-party vendors like IDEMIA and Cogent. The matching engines were essentially bolted onto the outside of the database. Stitching specialized external hardware onto a rigid legacy database to manage massive unstructured image files works for a while, but eventually the friction of moving heavy data through narrow pipes hits the absolute limits of computing physics. By the 2010s, the operational strain on IDENT reached critical levels. Federal agencies were adding millions of new queries daily, introducing entirely new biometric modalities, and demanding real-time results for border access. In 2014, the system suffered a severe security incident involving exposed contractor credentials. While no public biometric data was released, the breach laid bare the internal details of the architecture. Engineers saw exactly what the sheer volume of data was doing to the system's structural integrity. The event proved that IDENT had outgrown its original design. It was a fragile, single point of failure attempting to run critical national infrastructure. A simple patch wouldn't work. The entire architecture required a teardown. The replacement was named HART, Homeland Advanced Recognition Technology. Instead of building a slightly larger database, architects dismantled the monolith entirely, replacing it with a highly distributed ecosystem. Looking at this architectural diagram, we can see exactly how the monolith splintered. First, the clean biographic text was isolated and moved into AWS Aurora. This is a PostgreSQL-compatible engine designed specifically to multiply rows horizontally as text records grow. Next, the heavy physical biometrics, the fingerprints and face photos, were completely separated from the text. They moved into AWS S3, utilizing infinite, cheap object storage strictly designed to hold massive image files without straining the rest of the system. To find anything in that vast storage, architects introduced OpenSearch. By building a dedicated search layer entirely decoupled from storage, the system could retrieve specific files out of millions almost instantly. Travel patterns, aliases, and human relationships create incredibly complex webs of data. To parse these connections, HART utilizes AWS Neptune, a specialized graph database designed specifically for link analysis. Finally, the biometric matching engines themselves were rebuilt. Rather than relying on physical hardware appliances bolted to a server rack, IDEMIA's matching tools were rewritten as decentralized cloud microservices, actively processing streams of data on demand. HART overcame the fatal bottlenecks of IDEM by giving every data type its own environment. Biographics went to a text engine. Heavy images went to object storage. Relationships went to a graph database.
IDENT was built to hold records. It acted as a static filing cabinet. HART actively verifies reality, pulling multiple streams of continuous data to cross-check identities on the fly. The legacy system was engineered for an era of paper files and physical checkpoints, measuring queries in the thousands. HART measures queries in the millions, handling real-time global data exchanges and constant requests from mobile devices. Curious, forward-looking. When you look at an abstract 3D topographical scan like this, you see the true advantage of a decoupled system. If border security requires a new form of measurement tomorrow, like advanced palm prints or deep tissue scans, HART can simply absorb that future physical data. The ecosystem won't collapse because the storage layers operate independently. True enterprise scaling requires recognizing that a single, rigid box will always eventually break under pressure. Survival requires building an ecosystem of specialized tools that can evolve indefinitely. The massive scale of these databases remains completely invisible to the public. When a traveler applies for a visa or walks through a federal checkpoint, the Oracle tables, S3 buckets, and graph edges work silently in the background. IDENT represented the first generation of this technology, powerful, massive, and ultimately crushed under the weight of its own success. HART represents the cloud-native reality that replaced it. At this scale, identity relies very little on a name or a printed document. It relies on the instantaneous calculation of human biology, running endlessly across a decentralized cloud.